Being recorded.
Hello everybody, thank you for joining us today. Let me bring your attention from what you're working on and hopefully we can focus on our presentation. It's going to be a great one today for the next 45 minutes to hour. Let me introduce myself. I'm Kayla Berry, Quasi Communications and Outreach Specialist. And I just want to thank you for your participation today. We're about halfway through our spring Cyberseminar series. And like I said, this is a very interesting talk we have today, which goes nicely with our theme for this semester, which is complementary methods and models. Just to bring to your attention, we do have a few more cyber seminars this spring. One next week from Colin Bode at the University of California, Berkeley. You can find all information and recordings of past cyber seminars on Quasi's webpage. But I'd like to get to today's presentation, and before I start that, I do like to begin with getting information from our participants. If you wouldn't mind just typing into the chat box your institution, where you're from, location. I like to get a feel for who's on the line and where you're coming from. I do see a lot of new names today, so thank you. And then I will start with introducing our host for the series. It's Adam Ward from the University of Iowa, and he does a great job every week of introducing our guest speakers. So Adam, please take it away.
All right, well, thanks, Kayla, and thank you, as always, for all of your help setting up all of the infrastructure and working with our presenters to make these go as seamlessly as they do. Welcome, everyone. This is our fifth talk in a series of 7 this semester. Our theme this semester is complementary methods and models. And with that theme in mind, we invited Scott Miller and Steve Holbrook to talk to us about their work at the Wyoming Center for Environmental Hydrology and Geophysics. Their center was initiated in July 2012 as part of a 5-year, $20 million NSF grant with the specific goal of promoting scientific progress in mountain hydrology at the watershed scale using near-surface geophysics as a tool to link surface and subsurface hydrological models. And so with the themes of instrumentation, of methodology, and modeling, we really thought this was a great fit. Just a bit of a background on our presenters today. Scott Miller, his bachelor's degree is in geosciences from Brown University. He went on to earn Masters of Science and PhD degrees at the University of Arizona in watershed management, with an emphasis in a minor in remote sensing with his PhD. And he's been at the University of Wyoming since 2002. Steve Holbrook has a Bachelor's of Science in Geosciences from Penn State University. Earned his master's and PhD degrees in geophysics from Stanford, has been at the University of Wyoming since 1997, and is also an adjunct research scientist at Woods Hole. They've both got very long and impressive CVs, and so it's no surprise that they're running this new institute together. And with that, Scott and Steve, I'll turn things over to you, and my understanding is you're going to tag team the seminar today.
Yeah, thank you, Adam. This is Steve Holbrook, and Scott will jump in here in a minute. Hopefully, I want to thank everybody for calling in on this to listen to us. I want to thank Quasi and Kayla and Adam for inviting us to give this talk. Scott and I have been working together very hard over the last year and a half, almost 2 years since the proposal. So we're kind of used to finishing each other's sentences now. Hopefully, this won't be too much cognitive dissonance for the audience to listen to one person and then switch it off. We'll switch off a couple times through the talk, but Scott will start, so I'll turn it over to him.
Great. Well, thank you. This is Scott Miller, and I'll echo Steve's statements about thanking everybody for being here, and then just jump right in. We're going to start with an overview of the talk, just to give you a roadmap of where we're going to go. And when you see a name like WyCEHG, you always have to wonder how it's going to be pronounced and so on. This is WyCEHG, and I guess the answer is why not. But we'll talk about the goals of what we're trying to do. A lot of what we're after here at the University of Wyoming with this grant, we have 2 major areas of emphasis. One is to lift up the scientific community here and make us more competitive in this arena. That's a major supporting goal of NSF in this case. And we have scientific goals that are relatively broad-reaching, and we're going to touch on those today and explain and give some examples about how we are going about both integrated hydrology and geophysics with some specific local examples towards the end. give you a hint about what our science plans are and some preliminary results. So those are pictures of us out doing some activities. So you get a sense for what we look like in a Cyberseminar. So the WyCEHG itself is really an association of research scientists spread out across the university. You can see the text there. It's a fairly large infrastructure grant, $20 million. A little over half of that goes to research science, and then there's another branch of the grant which is intended to provide for education, outreach, diversity, and taking the information that is gained from science in the grant and making sure that it is disseminated throughout the state. So we are looking for statewide impact, and you'll see that we have research enterprises that are planned throughout the state, as well as partnerships with state, local authorities, as well as citizens and industrial partners. So this is not a typical research grant in the sense that individual faculty are given money to pursue an individual agenda. We're working as a large-scale team. You can see there are 8 departments, 25 or 26 faculty that are so far on the grant. So this is an institutional level grant, and again, the goal is to make sure that we are having impact beyond the individual faculty that are working on the projects. As part of that institutional development, we have planned for and have already started building 2 fairly significant facilities here that we intend to be nationally relevant by the time that we have built up this program. One is called FINS, the Facility for Imaging the Near and Subsurface Environment. That is where we house our geophysical equipment, of which you will get a sense in a few slides. We also have a hydrological lab, the Surface and Subsurface Hydrology Lab shell, and that is sort of where we house the hydrology and ecological equipment. These are not separated physically, they're co-housed. They each have a director who's responsible for managing the equipment, check-out, check-in, training, and so on. So these are commensurate facilities. They work very closely together. So you're going to see a lot of groups, a lot of people, but the overall theme that we want to impress on you is that we are striving to make sure that these are all integrated across both disciplines, physically and scientifically. So we'll give you a sense that there are private sector involvements, there's long-term research within the state, and at the end we intend to transition to a self-supporting national facility with Quasi being one of the backbones. So let's talk a little bit about science, which is of course the major rationale behind the WyCEHG side of this grant. We are charged with a couple of significant tasks, and in the West, as most people on the phone I'm sure are familiar, we are living in uncertain times. Especially in Wyoming, we have fairly significant landscape level changes that are affecting our environment, that are controlling the hydrological response, for which we are going to attack these problems with integrated hydrology geophysics. So our target areas for change within the state have to do with oil and gas development, bark beetle infestations, large-scale die-offs of forests across the region, and we are always faced with questions of fires and floods, and it would be foolhardy to ignore non-stationarity and climate change in any of these questions. We also have a major research initiative looking at snow. In Wyoming, we are essentially a snowmelt-dominated state with headwaters that are driven by winter events that then support our streams throughout the summer. So we're looking heavily at snow, instrumentation in mountain environments. But one of the themes is linkages across space and time, where we have snow and rain that is occurring in places that are far disconnected from where the water needs to be delivered for management. And so we're paying attention to teleconnections and impacts on downstream users for how things are going on up in the headwaters. And one of the overarching themes is tying all these together is trying to figure out new information, approaches, and models that can be useful to upscale from our observational platforms, some of which are points, some of which are lines, some of which are nodes on a map, to watershed scales and basin scales. And our approach that we will be doing that with is integrated systems modeling. We're partnering with our other large NSF grants here that is between the University of Wyoming and Utah that is charged with large-scale hydrological modeling. So we have a fairly significant high-performance computing part of this that is going to be our integrated outcome, I guess you could say. We're not going to talk a lot about the modeling today. We're mostly going to focus on some field efforts and some initiatives that we have gone forward for field observations in hydrology and geophysics. But if you're particularly interested in the modeling part, please feel free to contact us offline. So, key hydrologic questions associated with these broad themes of change. We really need to close the gap in the water budget. We've been studying mountain environments out in Wyoming for years, and we have a significant problem with closing the budget because the fate and transport of water in mountainous environments is very difficult to quantify. We have fracture flows that are poorly understood. The partitioning of water in the surface and the soil and groundwater is still an area of uncertainty. And that leads us into the idea that because of these gaps, we have disconnects between our observational information and what the downstream water users need. And so we are basically made an argument in our proposal that our surface observational platforms within hydrology and ecology are not sufficient to address these complex problems. So we need to couple our disciplines. We need to build better models. And that, in order to do that, we made an argument to NSF that we should be building a hydrogeophysics platform so that we could look into the subsurface and better describe the total system. So I'll hand it over to Steve.
Okay, thanks, Scott. So I'm going to talk a little bit about some of our new infrastructure. This is funded by some of you who aren't in EPSCoR states may be wondering what EPSCoR is and how in the world we got a $20 million grant from NSF for hydrology. And this is EPSCoR is a special program that it stands for the Experimental Program to Stimulate Competitive Research, and it's intended to sequester some funds solely for the smaller states that don't have large research infrastructures. And you can read the quote there as the purpose of it is to build sustainable improvements that make us more competitive in the future. What we're doing with this, so we're very happy to have brought some of that EPSCoR money over into the hydrological sciences, and hopefully the rest of the community will be happy about that too. So we're going to talk about the first two of these bullets, not so much about the third one in this short talk, but we'll give you a sense for what we're doing in terms of human infrastructure and physical infrastructure with this grant. So in terms of human infrastructure, we're pretty far along for just having started 9 months ago. We've already made our first faculty hire, a snow hydrologist named Nori O'Hara who came in from UC Davis. We have two outstanding facility managers, the two facilities, Shell and SINS. Some of you may know I'm actually a marine geophysicist by training, and so that we have to throw some nautical thing in there. So that's how we named our facilities. E.T. Elizabeth Traver is the manager of the hydrological facility, and Brad Carr is the manager of the geophysical facility. We have a search underway for a tenure-track hydrogeophysicist, and in future years we expect to hire an integrated modeler and a petrophysicist with the resources in this grant. We're also supporting a lot of grad students. A number of them are already on the grant. We have some more that we've recruited for next year. We're searching. We have one postdoc, Mehrez Wasif, and we have an open search right now. You can find in all the usual job listing places for postdocs in any of the fields that are associated with WyCEHG. So search those out or contact one of us if you or someone you know might be interested in applying for that. We have a lot of undergraduate research fellowships, and some of the results that I'll show you toward the end were actually acquired by undergrads working on our grant. And something else we'd like to inform everybody, one of the ways we want to bring expertise to help kickstart what we're trying to integrate here is with distinguished visiting sabbatical fellows. So we have, there's an ad that will be out in EOS shortly, and maybe some of you have seen it on some of the other listservs for sabbatical year fellowships. If you have a sabbatical coming up, and you might be interested in coming and spending some time in Wyoming, we can help cover the rest of the salary that your university typically won't for that sabbatical. We have divided our science up into 10 teams. We have a pre-organized structure. Each of the teams has a team leader. I'm not going to read through this in the interest of time, but you can look through and see the diversity of topics that we are covering here, and it's everything from observational hydrology observational geophysics, new method development in those areas, and up through modeling, component and integrated modeling. And there are some specific topics that we're going after, like bark beetle impacts, disturbances, and fluxes, as Scott mentioned earlier. All right, so a little bit about hydrogeophysics. Maybe some of you were tuned in for Kamini Singha's quasi-cyberseminar. This was a couple months ago. It was really good. I'm not going to try to, she gave a very thorough overview of what hydrogeophysics is. I'm in no way going to try to repeat that or duplicate it, but just a couple of words. It's simply the application of geophysics to solving hydrological problems, and you can see in the cartoon, as Scott alluded to, one of the major uncertainties in coupling surface and groundwater hydrology is to try to get the linkages between those reservoirs and systems, and that brings with it the challenge of characterizing the subsurface over large enough areas to get the flow paths. And you need wells to do that, but wells are sort of line sources in one place, and geophysics can help fill in the gaps. So the advantages of geophysics, as I see, and actually the left column is advantages and the right column is disadvantages. It looks like I didn't mean to imply that Burke-Minsley's figure was a disadvantage. So the advantages are we can characterize subsurface structure and physical properties over large areas. That brings with it the possibility of identifying potential flow pathways and where are the aquifers, where are the aquitards. We can make inferences about subsurface water distribution with some techniques like NMR. It looks like we could even characterize where the water itself is rather than a proxy for the water. Disadvantages are, with the exception of NMR, most of the bread and butter geophysical techniques are not telling us what we want to know. They're not giving us hydraulic conductivity or porosity or saturation levels directly. They're giving us some kind of a physical property that is a proxy. And so that means we have to have some kind of transfer function to go from those physical properties into the quantities that we want, and that's where petrophysics comes in, and that's why we have a petrophysicist on board. But the figure on the bottom is from a recent paper by Burke-Minsley and his colleagues, and it shows, I think it's up in the Yukon, and it shows some airborne geophysical data and conductivity structure in the surface, and they're looking at permafrost and how it's thawing, and looking at global change impacts on permafrost. So it's applicable over a lot of areas. And I'm going to turn it back to Scott for a few slides because he's the hydrologist.
Okay, so just to give you a sense for how we're building the physical infrastructure, we mentioned we have two different facilities, and in each case we want to populate these with both standard bread and butter techniques and emerging physical hardware and software that we will then be able to use to develop new techniques. And so what you're looking at on here is we have three general areas where we're building our hydrological both expertise and physical infrastructure. One, we have what might be considered fairly standard techniques for going out and doing nested watershed design with stream gauges and groundwater wells and flux towers and things like that. We're also investing in relatively new technologies for sampling snow, make sure that we're getting our students trained on all of the relevant technologies both for science and for jobs, so that when they come out at the end of their careers, whether they're undergraduate or graduate careers at the University of Wyoming, they are well trained and ready to go either to other institutions or to the job market. We are also doing a lot of work on a couple of hydroecological observations and tracer studies. We have an excellent facility here in Stable Isotopes that will help us bring field observational isotope real-time analysis into play. So that's going to be a very new technique that we're going to put in both on flux towers and in streams coming up in the next year. And we have high-performance computing at the University of Wyoming that is very, very high quality. The university has 20% allocation in the NWSC, which is a brand new supercomputing facility outside of Cheyenne. We're going to ladder ourselves up to that as well. So what we're trying to do in the hydrological community here is build everything from field observational platforms to high-performance computing and make sure that those groups are talking and guiding each other along the way. These are just typical pictures of things that we've already put into the field with observational towers for climate, eddy flux towers, and so on, stream observations. fairly standard stuff for hydrology, but the sense is that over the next few years, we're building both standard and emerging technologies.
Yeah, so Steve here again, back to the to geophysics. I'm not going to go into a lot of detail. We'll show you some data examples later, but I wanted to give those of you who aren't familiar with near-surface geophysical equipment just a taste of what that stuff looks like. Some of these pictures are from us, and some of them are just, from grabbed off of the web to show you what these things look like. We haven't purchased all of this stuff yet. We're still in the infrastructure building phase. We've purchased a lot of it, but so pretty much everything you can imagine in terms of bread and butter near-surface geophysical equipment, and even a few emerging technologies, we'll have at least one of here. Everything from ground-penetrating radar, seismic, electrical conductivity methods, the sub-bottom profiler up there on the upper right, that's actually a picture of ours going down through the moon pool in our the University of Wyoming's first research vessel. The CHIRP that can do sub-bottom profiling, magnetic resonance sounding. This is an emerging technology down there on the bottom right. Lots of other things, EMI, magnetics, complex resistivity, downhole logging tools. About half of these things we've already purchased or are in the process of purchasing, and the other half we will be purchasing over the next year. Now, and the thing I just want to make sure everybody sort of gets from these pictures is all of this stuff, pretty much all of this stuff is portable. It's meant to be the kind of thing you can throw in the back of a pickup truck and go out into your field area and do campaign-style measurements. So another thing that we're developing is a summer field course, a 2-week course. This is part of our education and our diversity bullets. We are going to be doing this jointly with Jackson State University from Mississippi. This will be happening in June. And I think that this is going to blend ecology, hydrology, and geophysics, which I think is emblematic of the theme of our center, is really to be interdisciplinary in a very meaningful way, not to have people siloed off and disappear back into their labs and their comfort zones, but really working with each other. And I think that's actually working very well so far.
Okay, so let's get into the science, which is sort of the key part to most interested people on here. So we did, as Steve just said, we don't want independent actors on a group like this. So people who are involved in this have been committed right from the get-go to making sure that they're willing to work together. And what you've got on the right there is a picture of what our conceptual synoptic approach to study, which is airborne. We have airborne geophysics coming. We have airborne LIDAR, potentially radar, other techniques for imaging from the air. And then at the same time, we have observational platforms in ecology and hydrology, tracer studies, and so on. And so when we go out and we mount our field campaigns, we may have 10 groups, but we will not be doing our job well if we don't pull it off so that we make sure that people are going out and committing themselves to data collection in an integrated fashion. All of the field data should feed all the project teams. We have basic agreements for publishing and so on, but the insights that are gained from an individual field campaign are being fed into a large-scale data management system, which will then become open access within the group and then eventually out to the larger hydrological community. That's a major part of NSF grants, as everybody knows, but we're going to be using some of the high-performance compute center options that we have here to make sure that these things are long-term data storage and then made available out into the greater community. Here's a slide of where we plan to be over the next 5 years. We're going to start local. I've got a couple of slides coming up on our Year 1 initiatives and some of the data that we've been pulling out of those. But you can see that this is intended to be broad brush across the state and going into areas that are of high impact. Over in the western part of the state, there's a lot of oil and gas development that has already been going on for decades, but in the next several decades continue. In the mountain areas, we have areas that are being affected by change of beetles and climate, and we are going to be making sure that our presence is felt in those areas so that we can track changes across time and space. And some of those initials that you see, NWC, AR, CC, those are some of our community college and other partners that we have brought into the grant from across the state who will be working both with us and independently leveraging some of our project monies. So, talking local now, in year one, the idea is that we will be building local platforms. And what you're seeing is a picture screen grabbed off of Google with the University of Wyoming, which is in Laramie. For those of you who don't know where we are, we're in southeastern corner of Wyoming, about 2 hours north of Denver, along the Front Range. And immediately to the west of us, it's about a 40-minute drive, there's the Snowy Range field site, which has high altitude, permanent snow, exposed rock, and so on. And then to the east, which is about 20 minutes away, is the Laramie Range, and we are establishing field sites there, which begs the question, why do you go local? And there are some very good reasons to do it. First of all, they're interesting research questions, so we're not just doing it as a matter of convenience, but we also have to have a matter of convenience so we can test bed all the equipment that we're getting. We also have a summer field course that we mentioned earlier, and people who are at the University of Wyoming teaching in these disciplines will be leveraging these field sites for individual courses coming out of the universities so that people can take students up, train them on equipment, use the data, and leverage it heavily. All of that speaks to having some local watersheds that are well instrumented, well documented, and so on. So we want to be able to test our ideas locally, make sure we're doing everything properly, and then launch out into the rest of the state. To give you a taste of what these watersheds look like and why we're there from a science perspective, these are the Snowy Range sites, which are to the west, relatively high mountain, 12,000 feet, with exposed rock and quartzite up at the top. Big glacial lakes, it's a relatively flat area. It was heavily glaciated back in the day. We have a nested watershed design with relatively small watersheds. You might call them zero or first order watersheds, depending on how you think about scale, where we are going to try to completely balance the water budget and heavily instrument them. And then all of the watersheds, as you go down out to the Little Laramie River, which is a large watershed, 400 square kilometers, will have nested instrumentation going down so we can do a good job tracking the fate and transport of water. Now, there are some very interesting things that happen as you go from the glacial lakes and Nash Fork down out to the Little Laramie River. You're going from very snow-driven systems, high altitude, high cold, through systems that are heavily fractured, down into plains and rivers that are heavily managed. And so throughout that, we have impacts of beetles, both in the pines and the spruce, so the vegetation characteristics have been changing significantly over the last 5 years and will continue to be in flux for the foreseeable future. And this is one of our homes for local field sites and the summer field course. And so we can tackle several of the large science initiatives that we are particularly interested in. So in the Snowy Range, our research initiatives that we're going after are looking at changes in melt and how it's partitioned into the Wyoming streams and how those changes that are being manifested across the landscape will result in changes in the hydrological systems. Because these are mountainous environments and there are a range of geological substrate, fractures, big glacial till areas, confusing subsurface, it has been hard to fully quantify and get the water balance right. So we are theorizing that we've got fracture control, and so we're going to tackle some of these scientific questions with geophysics and tracers. And we have very good local partnerships with the Forest Service, the Game and Fish. We're looking to work with private landowners, and one of our research scientists is the hydrologic extension faculty here on campus to make sure that we have good outreach as well, so that these information that we gain on the ground are then transmitted out to the relevant folks who are in the watershed. So looking over to the Laramie Range, this is to the east now, like I said, about 20 minutes. This is a nested watershed design that's been implemented. You can see that there are rain gauges out there. There's a snowtail site. That's not ours, obviously, but it happens to be pretty close. We have pressure transducers in a range of streams. This one drains off to the east and is one of the water supply systems for the city of Cheyenne. We also have a nested sample design with small watersheds leading to large ones. We have snow-dominated in the high hills. It's hard to call them mountains compared to the Snowy Range. We also think that there are fracture flows. This is a heavily managed water system. Some of the same questions apply in the Laramie Range. But the way in which we're tackling it is a little bit different because the scale questions are considerably different. So what we've got going on over in the Laramie Range is a nested design going from plot to watershed to what you might consider large watershed or small basin, and have established some natural rainfall runoff plots throughout the sites. 4 of them each has 4 plots. Each are outfitted with rain gauges. Some of them have more significant climate stations. All of them have soil moisture, and we can do surface and subsurface flow experiments, both with tracer studies and geophysics. So in the near future, we will be using these as local test beds to integrate some of the surface observations with subsurface geophysics. Now, we also have traditional flow metering going on in the watershed systems themselves and the stream channels. We have 2 big watersheds and then 5 nested sub-watersheds within them with the typical stream gauging system so that we can link up the rainfall climate with integrated runoff downstream. So why is this particularly a good place to go to hydrology and geophysics? We're going to spend the rest of the talk here in terms of science talking about why we're tackling this. First of all, even within this relatively small area, we have a high degree of variability in soils. The topographic relief is not extreme, but it's highly variable, so we can quantify it and tackle it scientifically. There are pretty significant microclimate changes across the landscape, and the vegetation ranges from fairly xeric uplands. We have thin soils in some areas. We have relatively deep soils in others. And beavers have altered the hydrological system in many of our drainages, which complicates things. It makes it a little more interesting to integrate the hydrological response. So we have variability from these xeric uplands to riparian habitats, and we have been trying to figure out ways to model it. And so that is, of course, a difficult problem, and as everybody who's in the modeling community knows, trying to capture the spatial variability across landscapes is absolutely critical to effectively capturing processes and representing flow. And so we are tackling this from an upscaling approach where we have plots to small watersheds to large watersheds, and we have run into some observational opportunities. We don't like to talk about challenges anymore, but there are opportunities for understanding better science. We have seen very little overland flow over the last few years, even in high rainfall intensity events, and I'll show you a slide here in a second, and very long lags in terms of how long it takes for water to process through the subsoil and show up in the river systems. And so that means that our models have not been behaving particularly well. We need to inform our models better and come up with better systems models. So let me just give you one example of an observational event. And what you're looking at, there's a circle on the right of the map. That's sort of the centroid of a fairly large storm. It did hit most of the watershed on the south side. And so the observational data that you're seeing are down on the south branches of those streams flowing to the east. And so this is a July event. As you can see, what you're looking at is a volumetric soil moisture on that green dot that's inside the red circle on the right. This is a pretty big storm, 2.7 inches. That's, for our part of the world, that's a lot. It can be almost a sixth of the annual water balance, depending on the year. And it was relatively high rainfall intensity, so 4 inches an hour. And what you can see is there was a response in the subsoil at the 15 centimeter depth and 30 centimeter depth that persisted for a couple of weeks and then disappeared again as water moved out of the system through a variety of mechanisms. The interesting point to take away here is that at 40 centimeter depth, we essentially saw no moisture at all sort of get through the system. So that implies that the penetration depth of that rainfall was relatively limited. 15 centimeters, you see it. 30 centimeters, it oversaturates the 15 centimeter depth and then goes back down. So when we look at the hydrological response in the stream that is just down from the kind of right in the middle, I guess you could say, of the centroid of the storm, you see this is a hydrograph, and if you're not familiar with the hyetograph, the little blue dot coming down for lines coming down from the top is up here. Oh, there it is. There's the rainfall coming down, so 2.7 inches of rain there, and then you see some overland flow sort of show up relatively fast. Within about 10 minutes of the start of the storm, we start seeing the stream respond comes up pretty quickly, but then the overland flow disappears relatively rapidly. There's very little of it. In fact, it's sort of less, it's in the range of 1% to 2% of the storm. And then you have interflow coming in through here, where over the course of about a day and a half, you have water moving out of the soil or coming out of the groundwater system, increasing flow in the stream. So that's a relatively small watershed. I'm sorry I didn't show how the size there, but we were relatively surprised because of the long time lag that are observed in a relatively small watershed, and there's a little bit of base flow increase from pre and post storm. And as we look down to the farther down river, this is the same. Now what you've got over here in this, I'll draw your attention to the right side of this screen. This is another gauge a little bit farther down river. You see the same kind of response, a little bit of overland flow popping up right away, and then sort of long lag flows coming out of the soil. And one of the things that we have been having a hard time figuring out from the modeling and observational platform is what those pathways are that are getting water from the surface to the subsurface, because of the way in which the soil moisture plots at the plot scale are sort of representing the hydrology. So that leads us to ask this question of how can we better describe the fate and transport of water as it goes from these rainfall events down into the, as they make their way through the soil and down into the stream. So one of the takeaway messages from the observational data that we've been looking at over the last year or so is that even with high intensity or high volume rainfall events, they don't get very deep. We don't see a lot of penetration to depth in many of our plots, and yet we see those sort of long-term release flows coming out of the soil. So our understanding of how the pathways are linked needs some improvement. So we know that a huge amount of our rainfall runoff events are dominated by lateral flow or soil or saprolite flow. Speaking as a hydrologist, I would like to know sort of a little bit better about which one of those are dominant and how that then will potentially play out as the vegetation changes and landscape management things are manifest on the landscape. So that leads us to the question of how might we tackle it from a geophysics perspective.
Okay, so Steve here again, and I'm just going to run through a couple of quick examples just to give you a flavor of what can be done in hydrogeophysics. And again, I would, if you really want a thorough overview of this field, I would point you toward the recorded version of Kamini Sinha's quasi-cyberseminar from, it was earlier this semester. It was really good. I'm just going to show you a couple of things that we've been thinking about. Part of the mission of our center is to try to help stimulate geophysical work in the critical zone observatories. And so with Cliff Reeby, I've been doing some sort of reconnaissance level geophysical work in the Southern Sierra, CZO in California. And what I want to just show you with this is something about how we might be able to infer porosity levels over a large subsurface area from geophysical data. And then I'll give you some, we'll return back to the Laramie Range where Scott just walked us through some of the mysteries of the hydrographs and show you how we might use geophysics to get a handle on some of those connections and subsurface pathways. So in the Southern Sierra Critical Zone Observatory, what you're looking at here is a seismic velocity picture on the, so I get this cursor working down here. The color scale is velocity over here. This line over here on the bottom right was collected over a granite outcrop, and what it tells us, this is all blue, it's all above 4,000 meters per second seismic velocity. That's what the velocity of the solid unweathered bedrock is in this area, and actually also in the Laramie Range. So wherever you see those colors down here in the subsurface, we interpret that as basically unweathered bedrock. So that means that everything above say the 4,000 meter per second contour here is something else. This is in the Providence Creek Watershed for the P301, for those of you who know this area. And right at the top of this hill is where the highly instrumented tree by the UC Davis group and others, CZT1, sits right there. Right over a place with relatively thick saprolite. And so these low velocities, the reds and yellows up here, are telling us that we have a pretty thick subsurface saprolite layer, lots of weathering. And it's quite variable. This graph up here shows the thickness of down to the 2,000 meter per second contour here and the 4,000 meter per second contour here. And you can see there are tens of meters of what we would call weathered. This would be saprolite, and this would be still not fresh bedrock. It would probably ring to the hammer if you hit it. It would look like a rock, but it still has significant porosity and therefore water storage capacity. And what we can do with this, one thing we can do, is we can apply a rock physics model. It's based on Hertz-Mindlin contact theory. And we can take those velocities and infer porosities, because especially in a place with uniform bedrock, which is one of the reasons the Southern Sierra CZO is so nice, and also the Laramie Range, there's not a lot of geological heterogeneity. We don't have to worry about going from a sandstone to a shale or a limestone or something like that. It's pretty much all granite and weathered granite products, which makes it, for a geophysicist, that's a beautiful thing, because it means we can infer porosities, and that's what this is. This is porosity on this scale, so fractional porosity up to 60% on this. And you can see that here there's quite a lot of porosity. And when we integrate that porosity over depth, we get this curve up here. This would be the total water storage capacity in the saprolite in this place. So in meters, or in other words, meters cubed of water per meter squared of area. So that's a significant and laterally variable amount of water storage capacity. And on the right here is just a comparison of our model porosity profile with depth at this line right here, and compared to these symbols up here are measurements from core samples, hand-augured samples from the UC Davis group, Armin Malaysian, Pete Hartzo, Jan Hopmans. And so we're up here, at least in the shallow part, we're pretty happy with this match. We don't have a lot of information yet from down here. But this seems like a pretty valuable thing if you want to understand where water storage could be and where the flow pathways might be. All right, so we're going to return to the Laramie Range, and I'm going to show a few slides, and then we'll wrap it up. And one of the questions we have up here in the Laramie Range, this is a photo of a place called Vitavu. Maybe rock climbers in the audience will have heard of this. It's a very, as you can probably imagine, looking at those cracks, it's a pretty well-known climbing area, especially if you like off-widths. And we have a question. When we look at this, you can see there are a lot of horizontal fractures, also a lot of vertical fractures. And one question we had is, well, what does this look like in the surface beneath the weathering layer? And also, could we image these features? You would expect that if these features exist in the subsurface, they would play a strong role in guiding subsurface flow. So the fundamental geophysical imaging question is, can we see them? So I'm going to show you what I think these things look like in the subsurface. This is a radar image done by one of our grad students. It's not in the exact same place, but you're looking at about 6 meters in depth and about 75 meters across. It's about the size of a football field across, so there's some vertical exaggeration here. And up here in the Laramie Range, it turns out to be just a beautiful place to get radar images of these features. So what we're looking at, this is all granite and weathered granite products, saprolite up above it, very thin soil layer. So we believe that all of these features that you're seeing here, both these strong subhorizontal things, and even there's some more steeply dipping things coming through, like here and here. These are probably, I mean, they could be, some of them could be dikes, original fabrics, and compositional changes in the batholith, but probably most of them are fractures, that are sort of mimicking what this looks like. And we do have one place where one of our students James went over an outcrop where you could see it, and in fact, these kinds of strong reflections are exactly what those things look like. So we think this is pretty cool because up here we can image these potential subsurface pathways. So just zooming in, I'll point out that these two colored polygons here are where we will be acquiring airborne geophysical data this summer with the SkyTem group from Aarhus, Denmark. We're going to zoom in on the Laramie Range there. Zoom in again up here in this area called Coyote Rocks. There it is, and here you can see one subset of some of the GPR transects that one of our undergraduate research fellows, James Ramsey, acquired in here, and it just goes across the top of a little drainage here, and James has been trying to map out some of these subsurface fracture features. You can see there's some nearby outcrops on the surface, but by and large, this is a pretty large area with not a lot of outcrops. just an upland terrain of weathered saprolite. So here's what this looked like. This was just last Sunday. The results I'm about to show you we just got last Sunday. Up here we're collecting seismic and electrical resistivity data as well as EMI data up here with some students in a class. And all the results I'm about to show you were done pretty much by students since Sunday. So here's the original GPR transect. And you can see some strong subsurface reflections. It looks a little different from that other site. There are some areas where there are some subparallel dipping reflections over here and over here that really stand out. There's a very strong subsurface reflection that's within a meter of the surface over here. And James Ramsey, one of our undergrad research fellows, had the idea of going up here and digging a soil pit and looking to see if we could ground truth this very bright reflection. And it turned out to be a beautiful thing. Here's the pit that he dug. 80 centimeters, 81 centimeters down is this layer down here, which you can see it kind of makes a shelf on there. It's surrounded by this grist-like stuff, this weathering out saprolite. It's a clay-filled layer. Zoom in. Here's what it looks like. You can see the layer going right across here. And that is exactly at the depth predicted by the radar, and it seems to be a clay-filled fracture. So that gives us some ground truth and also some modeling and predictive capabilities for the radar data going forward. So on this one, we have picked some of these. You might see some of these major reflectors are highlighted. So those are going to be markers in some of the comparative integrated images we'll show next. So, whoops, that is on its side. I don't know if that's looking like it's on its side for other people or not, but I'll see if I can. Can somebody type in there if this is looking like it's not oriented horizontally, so I know. This is sideways. Okay, so everybody turn your heads to the right, and this is the resistivity model along that transect. And what we see here is, so this is the gully, and here is a conductive layer in the surface, and then there's a layer that goes along here that's more resistive, and it's got a couple of breaks. There's one that goes down to depth like this, another one that goes down kind of over here. And man, these are all going to be sideways. If these are compared to the radar reflectors, which are these up here that have just appeared, there is a really nice correspondence between these resistivity structures, so where things are more electrically conductive, these colors, and more electrically resistive, the red colors, there's a really nice correspondence, and in particular, these dipping features that we believe are fractures and that we know is a clay-filled fracture right there, these things are dipping down to the left here and here in these channels where this resistive layer is broken. And so they're more electrically conductive. That's hinting that they may have some water content. It might just be the clays in the fractures. We can't be sure. But we would propose that this would be a great place to go do a sprinkler experiment and some time-lapse and really test whether water that's coming in at the surface can make it down through these pathways. And the correspondence with the data sets, that's how it's supposed to be oriented, is really nice here. In terms of the seismic velocity, the contours kind of go straight through. There's not a lot of, and these are pretty low velocities, 0.5 kilometer per second, 1 kilometer per second, down to a 1.5, which is telling us basically, it's telling us, I think, two things. One, this is all very highly weathered saprolite, a lot of porosity. And the other thing is, seismic velocities aren't very sensitive here to fractures and what's going on. There have been some papers that have come out that suggest that if you see low velocities, low seismic velocities in the near surface, you can interpret that as a higher concentration of fractures, and we might need to use a little caution in making that interpretation. However, there's some new, this one's oriented the right way, there's some new results that James St. Clair, one of our grad students, has been working on, trying to extract more information from the seismic wave field than just the travel times and the velocities. In particular, he's written an approach to do seismic attenuation tomography. So what you're looking at in these colors is just a map of where, in the yellow and red colors, where seismic waves are most attenuated. That is, they lose the most energy on their way through the subsurface, and the blues are places where they don't. And there are some hints. This is still very preliminary. We're not sure exactly what this means, except that there are some hints that some of these more fractured places look like they have higher seismic attenuation. So this may be telling us that we could glean other information from the seismic data that might, than just the velocities, that might be pointing towards things like the fractures. So just to sum up now, what we're hoping to establish with WyCEHG are nationally significant facilities in near-surface geophysics and hydrology, and those are very linked activities. The near-surface geophysics is the linking activity between surface and subsurface hydrology for us with this center. We're building interdisciplinary cross-institutional teams in Wyoming that are focused on hopefully transforming water research. These are the kind of words you always put in your NSF proposals. Hopefully we'll have a shot at doing this. Scott alluded to, there's a very strong external engagement program, education, outreach, diversity programs. We have a workforce development program that's going to train students, and we have a couple of environmental industry companies that have signed on, and they're hiring our students at their expense for internships. And ultimately, we'd like to make this an open access national facility for hydrogeophysics. That's not going to be happening in the first couple of years as we're just building it up and using it for all the science we've promised to do in the grant. And we also have an industry endowment of about $670,000 from Marathon that will provide in perpetuity funds to support the maintenance and upkeep of the geophysical facility. And we're going to be linking very strongly with the new NCAR Wyoming Supercomputing Center, which, as Scott said, has just moved up to Wyoming. So one of the slides, I won't tell you how late in the last night or in the morning Scott and I were working on this PowerPoint. And one slide we forgot that got left out is acknowledgments. So I want to say a few things about some of the people that have helped us. Scott and I tend to give a lot of these talks together, and we get to act like this is our thing, and we get to get some credit for it, which is really not fair because this has been a huge effort on the part of many people. And first and foremost, the lead PI of the $20 million grant that we received is Dr. Ann Sylvester. She is a microbiologist, a very successful scientist in her own right. She's also the director of the Wyoming EPSCoR program and the lead PI on this grant. Scott and I are the other two more junior PIs. And the Wyoming EPSCoR office that Ann runs, the folks in that office have been extremely helpful in getting the center off the ground and keeping it moving and keeping the rest of us on task. We also need to thank the University of Wyoming. This is really not a $20 million project. It's a $24 million project because these research infrastructure improvement grants from EPSCoR require a 20% university or state match, which the University of Wyoming provided. A lot of faculty, staff, postdocs, and students within WyCEHG and all the associated departments have contributed enormously to writing the proposal and outlining the research goals and getting the work done. We obviously want to thank NSF for funding this and all of our collaborators around the state and the country. And with that, I think we'll stop and open it up for any questions if there's time. Thank you, everybody, for listening.
Yeah, hi, this is Adam. Thanks very much, guys, for a great presentation. It was a really nice overview both of what you're building towards and some nice demonstrations of why we need this kind of information and the rationale behind it for us as a community of hydrologists primarily here at Quasi. So I'll do my best to try and moderate a bit of a question and answer period if you guys all have some time. So folks with questions, if you want to type them into the chat box, I'll do my best to take them in order, and then you can certainly feel free to unmute yourselves to clarify or ask any follow-ups that you need. So if folks on the line want to type anything into the chat box to ask, that would be great. And I see we have a question that Doug J. posted during the talk. Says, who does a prospective grad student contact if they want to be part of this WyCEHG operation?
So great question, and so there is a PhD program in hydrology here, which Scott Miller, my colleague here, is the director of, and part of the purpose of this grant is to build that program in the way that our last big NSF EPSCoR grant built our program in ecology, which is now off and running and very successful. So Scott would be a great first point of contact. But not all of the students that are supported in WyCEHG, because it's such a diverse program across several colleges and many departments, we're trying to get a good number of students in the program in hydrology, but some of the students working on the grant are just enrolled in the respective graduate programs in the departments. So the geophysicists are in the Department of Geology and Geophysics, and so, it's a normal, you can apply through the normal channels in the department that you're interested in or in the program in hydrology, and just, I would say, in your application, just make mention of WyCEHG and you're interested in getting involved in that research.
Thank you. And let's see, Henry Lynn up at Penn State, I believe, is wondering if there's any pedologists or field soil scientists involved in your ambitious effort.
Yes, and good question. Can't ignore soils whenever you look in the subsurface. And we have 3 people who are on the project who are trained as soil scientists, broadly defined. One is Thijs Kelleners. He runs our systems modeling group. He's a soil physicist and does observational soils. Historically has done them sort of at a point and vertical transport dominated modeling. He's done quite a bit of watershed scale upscaling as well. So he's one of our soil scientists. Ginger Page was also trained as a soil physicist and as a soil scientist and works as a watershed hydrologist extension. Also we have Elise Pendle, who's one of the cooperators over in botany, and she has a very good, strong background in soils as well. So those are people who core on the team, and then, we name a lot of people, but then we leverage like crazy. So we are working with other soil pedologists. Larry Munn's been out in the field with us, very expert guy, and so on. So we sort of reach across disciplines to make sure that we're pulling in the expertise as much as we can. But we do have people who are core on the project who are trained in that discipline.
Thanks, guys. So this is Adam. I'll just take the prerogative. Maybe throughout your talk, I noted down several opportunities for people to get involved, several sorts of data sets or facilities that are out there. What are some of the easiest ways for someone to get involved with working at your field site or working with your data sets?
Oh, excellent question. I guess we haven't really established formal mechanisms yet. One of the reasons we'd like to give talks like this is to make sure that people who are in the broader hydrological or geophysical community, or eco-hydrology for that matter, know that these things are coming online. We have already started to build some of the larger scale field exercises, but we also want to partner with people in the sense of building more collaboration and more grants and more infrastructure beyond what we are talking about. If we were to spend 5 years working on this grant and hit a bunch of our research outcomes and then stop, we would not be successful. What we are trying to do is leverage our capacity building here through the field observational data. That's one mechanism by which people can come involved, like get involved, basically find a point of contact on the grant and make a link. I mean, that's the absolute simplest way to do it. But, down the road, what we would really like to do is leverage these approaches to build more grants and more opportunities from the state. EPSCoR and NSF are funding us in order to build our ability to do just that. So we've had 3 go in this year to NSF and DOE that are basically leveraging on this opportunity with partners both in and out of the university. And that, I think, is probably the greatest mechanism that we'll promote over the next several years. That's not to say people can't come on and use data and so on, but we are also looking to make sure that we're building the program beyond the scope and scale of what we're setting out to do.
Great. Let's see, and we've got a question. Jiabing Zhao from Montana Tech asking about, says, you mentioned visiting sabbatical fellows. How does that work? How do I apply? Are only Wyoming faculty eligible?
Definitely no to the last question. The entire purpose of our visiting sabbatical fellow program is to help jumpstart some expertise that we don't already have in Wyoming for the project. So you can certainly contact either Scott or myself, but keep your eyes open for this. Will be coming out, I believe, it'll be in 3 issues of EOS, the ad, in late March and late April and early May. So it's about to be advertised, but it's absolutely for faculty from anywhere who are interested in coming here and getting involved in our science in a sabbatical visit here.
And just as a point of order too, we try to keep all these things current and posted on the WyCEHG webpage, which if you just Google WyCEHG, you find it. But it's basically uio.edu/WyCEHG. And so any of these kind of opportunities, we make sure to have them so that people who are visiting can identify them.
Sounds great. Well, if there's any last-minute questions, please go ahead and type them in the chat box. I see folks are starting to sign off a bit. We peaked around or a little over 40 today, which is a great turnout. And Scott and Steve, I wanted to just thank you again for letting us know what you're working on and presenting some opportunities that hopefully got us thinking about science as well as about visiting Wyoming.
Well, thank you, Adam, and yeah, thanks for giving us this opportunity to tell you guys about what we're doing. It was fun.
Absolutely. Well, we'll hang on for 1 second. If there's any last-minute questions, either shout them out or type them in. Otherwise, I hope everyone has a great weekend, and hopefully we'll see you here in a week for our next seminar.
And from Quasi side, I just want to say thank you again to everyone who joined us, and thank you to Scott and Steve. It was a great presentation. We look forward to working with you from our side.
Great.
Great.
Thanks, Kayla.
Thanks very much.
All right, have a great day.
All right, bye-bye.
Bye-bye.
Goodbye.